In this video, we're going to talk about trig identities that can be established using either translations or symmetry, i.e. even and odd function concepts. Well, to begin, let's look at the function y equals sine x, which is shown in thin ink, and let's also show the graph of y equals cos x, which is shown in thicker marker. Perhaps you can see that if we were to take the thicker marker curve and translate it 90 degrees, i.e. pi over 2 radians to the right, it would exactly land on the thinner inked curve. So again, take that thicker inked curve and just move it to the right. It'll fall on the thinner inked curve. In other words, if we take the curve y equals cos x, which is the thicker one, and translate it a bit to the right, we're going to get y equals sine x. So in other words, what we can say is that y equals cosine of x minus pi over 2, i.e. translated pi over 2 units, pi over 2 radians to the right, will then be the same as y equals sine x. It also works the other way. If we take the thinner inked curve and we translate it pi over 2 radians to the left, we're going to land on the thicker curve. So if we take sine x, and if we translate it pi over 2 units to the left, we're going to end up on the curve cos x. So this is rather interesting, and so it leads us to a couple of very useful trig identities, that the cosine of theta minus pi over 2 is equal to the sine of theta, and that the sine of theta plus pi over 2 is equal to the cos of theta. Okay, and those are trig identities that are related to translations. Now, let's talk about trig identities that are related to symmetry. And before we go too much farther, just remember that something that we learned early in the course was that if a function has rotational symmetry about the origin, i.e. if we can take a function and rotate it 180 degrees around the origin, and it falls back on itself, then we call that an odd function, and it has the property that f of negative x is equal to negative f of x. On the other hand, if we have symmetry about the y-axis, then that's called being an even function, and when that happens, we say that f at negative x equals f of x. Okay, so if we can rotate a function 180 degrees around the origin and have it land upon itself, then we know that this algebraically is true about that function. On the other hand, if we can take a function and reflect it in the y-axis and have it land back on itself, then we know that this is true about the function. Okay, so keeping that in mind, let's look at the curve y equals sine of x. Well, take every one of these points on y equals sine of x and rotate it 180 degrees around the origin, and you're going to get a point on y equals sine x. Take this point right here, rotate it 180 degrees about the origin, it'll be here. Take this point, rotate it 180 degrees about the origin, and it'll be here. In other words, the curve y equals sine x has rotational symmetry about the origin. And as we just reminded you, when a curve has rotational symmetry about the origin, that means that f at negative x equals negative f of x, which is what's written right here. Well, in this case, f is sine. So what we can say is the sine of negative theta is equal to negative sine of theta. And that's a good identity for us to remember. Now, perhaps a little bit easier to see is when there's symmetry about the y-axis. So let's look at y equals cos x. This curve, if we reflect every one of these points in the y-axis, we get a point that still falls back on the other side. Therefore, this is an even function. Symmetric about the y-axis means that y equals cos x is even, means that f at negative x equals f of x. Well, that means, since f in this case is cos, is the cosine function, that the cosine of negative theta equals the cos of theta. Finally, this is what a curve of y equals tan theta looks like. Okay, interesting looking curve. Well, if we were to look at every, this curve is actually rotationally symmetric about the origin. If we were to take this point right here and rotate it 180 degrees, it would land here. If we were to take this point and rotate it 180 degrees, it would land here. Believe it or not, if we were to take this point right here and rotate it 180 degrees, it would land here. And so every single point on this curve is rotationally symmetric about the origin, believe it or not. And so what that means is that if your function is tan, f at negative x equals negative f of x, which means the tan of negative theta is equal to negative tan of theta. And putting all that together, we can make these three identities clear to ourselves as well.